All right, let's take a look at our lesson for today. All right, so we're going to take a look at squeeze theorem and trig limits today. Let's focus on squeeze theorem first. Now, the name squeeze theorem, okay, so some textbook calls it squeeze theorem, some textbooks call it the sandwich theorem. I just really like the squeeze theorem. I don't really like to think about a sandwich because then that makes me hungry maybe. I don't know. We're going to go with squeeze theorem, okay? But just know that it might be referred to as the sandwich theorem also. So let's talk about what we need to be able to use this theorem. All right. So first of all, we have to have an inequality that's set. Here, they're saying that f is the smallest function and g is in the middle and then h is the biggest one. So we've got to have, we have to have an inequality to be able to use this theorem. And we are typically given that inequality. What the theorem tells us is that if the limit of the little function is the same as the limit of the bigger function, they have the same limit, then the limit of the middle one will match. That's basically the theorem. This is a visual picture of the theorem. So if you look at it, you see the red curved h is always taller. Right? It's bigger than the other two. So this one is the big one, H. So then the smaller one is F. That one you can see all the Y values are lower than all the other ones. And G is the one that's in the middle or is stuck in the middle of it, squeezed in the middle. And so that's a visual picture of what that theorem is telling us. All right, questions so far on the concept, just the concept of what in the world they're talking about. This theorem is what we use is for limits. We use this theorem, the purpose of it is for limits. Okay, so this would be for limits. Sometimes they'll tell us to use it, sometimes we will be able to figure it out. Now, how would we be able to figure it out? Let's look at our example on this. So as I look at this inequality, so they give us an inequality right here. We see that this one is the small one. That's the one that's smaller. 4x is the one that's smaller than all the others. This one right here is the one that's larger. And then we have this random, this f of x is in the middle. We don't really even know what the equation of f of x is. We don't know anything about it. So this is one of the scenarios where it's helpful to have the squeeze theorem so that we can actually solve a limit of a function we don't even have the equation for. So what do? How does this work? What we want to do is we want to take the limit of the little one, so the limit of the small one. So let's do that. So the limit, and this is the value we're looking at as x goes to 2. Okay, so the limit as x goes to 2 of the small one of 4x. Let's think back to our limit rules. Remember, the first thing we do is substitute the 2 in or plug it in. And 2 times 4 is 8. And if we plug it in, get a number, we're done. So that's the ideal situation. We know that doesn't happen a lot, but that's the ideal. So the littlest function, the limit as x goes to 2 is 8. Let's check out the biggest one. So the limit as x goes to 2 of x cubed. Again, we're doing our limit technique. So we take the 2, we substitute it in. 2 cubed, let's see, 2 times 2 times 2. 2 cubed is 8. And so now we see that the limit of the little one is 8 and the limit of the big one is 8. So therefore, we can say with confidence that the limit as x goes to 2 of f of x, which, we don't know much about, but we do know that its limit at 2 is 8. And we could say by squeeze theorem. Now, it's okay if you don't remember the name, and it's okay if you don't write by squeeze theorem. That's okay. As long as you show the parts of the squeeze theorem. So we showed the limit of the little one and the limit of the big one are the same. Then we can take from that the limit of the middle one is the same as those. So I want to pause there for a second. That's basically the squeeze theorem. There's really not much more to it than that. Okay, yes. Oh, so good question. So there's a couple of things with that. First of all, sometimes the inequality that we're given, it only is good from, say, x is -1 through 1, something like that. Sometimes they limit it for us. This one, they did not limit at all. And in the case where the little one and the big one, let's just say, for instance, that when we're trying this theorem out, let's say that the limit of the big one was not 8. If that's true, then we can't use the theorem. We would just have to say the theorem does not apply. Squeeze theorem does not apply. And we wouldn't be able to go any farther than that. Does that make sense? So we're expecting the limit of the little one and the big one to come out the same. That's what we're expecting to have happen. But if it doesn't, then we can't use the squeeze theorem. Okay, anything else? Okay, so the second topic that we're looking at today is trig limits. Yay, trig! Oh my gosh, I love trig. I know I'm probably maybe one of a handful of people in here, or maybe the only person that loves trig. I don't know, but I love trig. So let's talk about these special limits. These special limits are limits that you would need to memorize. They're on the formula chart. And they have some peculiar things that happen. So what I want to do is I want to explore each of these limits separately. Okay, let's just look at them because they can appear differently than they look now. So let's show this one, this first one, and of course it's sine. Sine is so nice. This one is very flexible, very flexible. So let's just write that. I'm just going to write a note. So this one, this particular function is quite flexible. Now let me show you in which ways it's flexible. So this certainly is true. The limit as x goes to 0, please note that x is going to 0 in this scenario. The limit as x goes to 0 of sine x over x is 1. If we were to substitute the 0 in, it would give us sine 0 over 0, right? Which we know we wouldn't be able to do anything with. So this is a special limit that allows us to deal with sine 0 over 0. Okay. Now, let me show you how it can be adjusted. So, for example, this, and let's write with it. So this would be true also. The limit as x goes to 0 of x over sine x. That's also 1. It's okay. This one you can flip upside down, and there's no problem with that. In your limit work, you might see it like that. That's okay. Another way that it can be altered, the limit as x goes to 0 of, let's say, sine of 3x over 3x. That's also 1. That's kind of nice. Please note on this one that these spots, this 3x, they have to match. Those spots right there in this scenario must match. And when I plug a 0 in, it should be 0. It should be sine 0 over 0 when I sub in. So it could have been sine 4x over 4x. That's still 1. Sine half x over half x. That's still 1. Very, very flexible. We just have to recognize the pattern. The last one, which is the craziest one of all, I think, if you'll notice, all of these are the limit as x goes to 0. That's what this is. It is actually possible. This one is so flexible that it could also look like this. The limit as x goes to 1 of sine x minus 1 over x minus 1. That's also 1, which is totally weird, right? We're going to 1 this time. How is that even possible? Well, what happens when I substitute a 1 in there? I get sine 0 over 0. That's the pattern. But again, I'll make a note of this again. These things right here must match. This is not doable, so that part, those parts must match, or this won't work. Okay, it's not just the sine 0 over 0 that's going to do it for us. Those two locations have to match. So this little guy, this is the really flexible one. Okay, we got all kinds of fun things that can happen with this little one. Very flexible. The other one, the cosine one, is not really very flexible. I know, big surprise, right? For those of us that kind of know their personalities, like, yeah, not very flexible. Not very flexible. First of all, you can't flip it upside down. It does not flip. It's not a thing. It will not flip upside down. You cannot do that. So if you see this one flipped upside down, you cannot use this special limit. It just won't work. Okay, can't do that. Now we can do something like the second one where, so the limit as x goes to 0 of 1 minus cosine 3x over 3x. We can do something like that, and that's okay. Right? It'll handle those. It'll handle adjusting the argument of the cosine and the denominator. It's okay to have those same numbers. But again, I'll just point this out, ladies. These have to match. Those spots have to match. Okay? They must match or you can't use this. That's just about as crazy as it gets. I mean, there is one other thing which I see every once in a while. It is okay, the limit as x goes to 0, it is okay to reverse and say cosine x minus 1 over x. Because that's basically negative 0, which is, 0. So that's really as flexible as that one gets. This one is not as kind and generous and helpful as the sine one. It's just not. So, but I'm going through that in detail because it's important that we understand how they work before we try to utilize them in our work, okay, in our limit work. Yes, ma'am.
Did you help with the x minus 1 on the cosine of the cosine?
Oh, the x minus 1 and on the bottom, the x minus 1. Yeah, those two locations you can adjust a little bit, but that's as good as it gets. It's as good as it gets. Okay. Are we okay? All right, so let's work some examples. So this first one is not a trig function. It's just a trig limit. It's just getting us used to just more practice with left and right-sided limits and piecewise. We've already worked on this before. It's just another example. So as we look at this, we see that this first one, we going to go to 1 from the left. And the left is going to be where 1 is, small, right? We're coming from the left. So for that one, we need to use the first branch. So the limit as x goes to 1 from the left, and we'd use the negative 2x plus 4. That's the piece we would use because that's the part that would come from the left side. Right? So we've got our, number line. Here's 1. As we're coming from the left, it would be the negative 2x plus 4. That's what we would have, if this helps conceptually. And then coming from the right, it would be the square root of x minus 1 coming from the right. That's according to how our piecewise is set up. If that's helpful to write it in that way, I encourage you to do so. So when we have one-sided limits, we're just plugging in a 1. And the only time we would have to deal with that is if we got something weird like 0 over 0 if we plugged in a 1. But when I plug in a 1, I just get a number, right? I'm just going to get a number. And so I've got negative 2 times 1 plus 4, and that gives me, what, 2. So the limit as x goes to 1 from the left is 2. Okay? Now let's focus on the one coming from the right. The one coming from the right is going to be from the big side, right? From the, you're bigger than one side, so you're coming from the right. So we've got the limit as x goes to 1 from the right, and we're going to use that bottom piece of the piecewise. So we substitute a 1 in there, and we get the square root of 0, which is 0. Now we've done the two one-sided limits. Okay, let's focus now on, recall, this is called a two-sided limit. Or I like to say a full limit. A full limit or a two-sided limit. Remember, for a two-sided limit, if for it to exist, what has to be true? Exactly. That's one of the rules that we learned, right? The limit as it approaches from the left and the right has to be the same. Are these limits from the left and the right the same? They are not. So we would say, therefore, and our reasoning is written above. Therefore, the limit as x goes to 1 of f of x, d and e. And when you do d and e, please don't say equals d and e. Just do an arrow. Because you can't really equal something that doesn't exist. Does that make sense? We can't equal something that's not there. Okay? And that's just another example of our two-sided limits. Okay, and piecewise functions. How are we doing? Okay, so now we're going to jump into trig. Oh my goodness, I know you can't wait, right? We're going to get to use all kinds of trig identities, like, oh my gosh, it's going to be so great. We're going to use like Pythagorean. So remember, sine squared plus cosine squared is 1. Remember that business? So let's look at this first one. I have a fraction, so let's just get into the habit of doing the limit as x goes to 0 of the top, sine squared, over, let's just get in the habit of doing our limit laws and breaking that apart. That's just going to serve us well in the future. If we're just in the habit, let's just be in the habit of that. Okay, when we have fractions, we should write it like this. That's preparing us for our lesson to come on L'Hopital. So let's see. Remember, sine squared means sine times sine, right? I hope we remember that from trig. We may or may not. This sine squared means sine x times sine x. I mean, that's what it means. So if I sub a 0, we need to think unit circle value. Sine of 0 is 0, and 0 times 0 is 0. So this limit of the numerator is 0. So unit circle values, plug in a 0 for cosine. Let's see, cosine of 0. Cosine of 0 is 1, so 1 minus 1 is 0. So this is one of those type 2 limits where we sub in and we get 0 over 0 or infinity over infinity. And when we get that, it means keep going. Keep going. Let's think about the 4 things that we talked about before. Let's just put out to the side. We had the things to do. We had factoring. That was a thing to do. We had multiply the clever form of 1 business. You know, multiply a form of 1 like a conjugate maybe. We had fractions like fixed fractions or common denominators. Remember, we had a common denominator, and then we also had like fix a complex fraction. And then the 4th one was trig identities. Looks like that's where we're going to be landing here, is trig identities. In order to work this, we need to think of a way, and you guys know how flexible trig is, right? We got all kind of things going on with trig. So it's okay if you try something and it doesn't work. You just need to try something else, because there's several things I could think of to switch this to. But I've got a sine squared, so I'm going to use the Pythagorean theorem, the Pythagorean identity, and we know that sine squared plus cosine squared is 1. So that means that sine squared is 1 minus cosine squared. So I am going to replace sine squared with 1 minus cosine squared. Now, it might not have, maybe that's not the first thing you would try. It's okay. There's more than one way to do these. There's not just one right way. All right, so please know that you can try many different things. There's not just one right way. This is what I would try, and so I'm going to replace sine squared with 1 minus cosine squared. And I have 1 minus cosine on the bottom. Now, please don't, like, we know we can't cross because there's a minus in there, right? There's no crossing out from top to bottom. But I can factor the numerator. Now, is this just crazy talk for us? You're like, what? Factor the numerator? I could factor it because it's like, I'll just put this in like a little different color. So this is like 1 minus x squared. This is what it's like. That's what the top is like. 1 minus x squared factors to 1 minus x, 1 plus x. Right? This is perfect squares. Right? That's what it's like. Okay? So when I factor it, so limit x goes to 0, I factor it as 1 minus cosine times 1 plus cosine. Okay, does anybody see anything we can do now that we have it factored?
Cross out.
Cross out, absolutely. We can cross that out. And if we want to rewrite that, it's perfectly fine. Limit x goes to 0 of 1 plus cosine x. So limit of 1 is 1. Plug in a 0 to cosine, I get 1. And 1 plus 1 is 2. Who knew that 1 plus 1 could be so hard, right? 1 plus 1 is 2. But we had to go through the trig to get to it. All right, how are we doing?
How do you know that the cosine of 0 is 1?
Unit circle value. So you're here at 0. We know that on the unit circle, that's 1, 0. So unit circle value.
Okay.
And cosine goes with the x, so cosine is 1. Uh-huh.
For our test, are we have those formula sheets for the outcomes?
No, they need to be in your head. Yeah, they need to be in your head. So here's why. Because, all right, so how are we doing on this one? Are we okay? All right, so let's look at, I think I have a couple more examples. A couple more, so let's look at these. See what we got going on here. Oh my goodness, that is so close to the special limit, right? That is so close. I wish I wish I could cross out the sine x and put 2x. Wouldn't that be just delightful? Yeah, but we can't. We can't. So, again, there's several ways to do this. You could think about cosine 2x, this double angle, and try to switch it out and do all kind of stuff. You could. I didn't do it that way, but you could try that way. I'll just show you the way that I thought of doing. You could say, ooh, if you don't have anything to do, you could just try different ways on your own. Wouldn't that be fun? Like, oh yeah, let's just do double angle or whatever. Okay, never mind. I'll try to calm down. So instead, what I would do on this one is I want to use my limit laws, and I want to split this apart because I'm always thinking about how I can use the special limits. I'm always thinking about that. So I'm going to pull this out, cosine 2x over 1, and I'm just going to show them as being separate. Because I really wish they were separate, right? Because we've got one of the limits that's like 1 minus 2 cosine, or 1 minus cosine over x, and the other one is like sine x over x. So that's what I'm hoping for. So after I do that, it occurs to me that I can multiply by a clever form of 1, and that clever form of 1 is x over x. Now, why would I think about that? Well, because I want an x underneath the 1 minus cosine, and I want an x on top of the sine. Why would I want that? Why would I want that? Why would I want an x underneath the 1 minus cosine? So I could change it, right? So I could change it, use a special limit. And why would I want an x on top of the sine? So I could change it to the special limit, right? That's what I would want. So that's what I was thinking. Again, this is not the only way to solve this. So I'm going to limit x goes to 0. So I've got 1 minus cosine 2x, and I'm going to make, where this is all multiplying together, right? All multiplying. It doesn't really matter the order I do it in. And so I have gotten, I've got what I want. So just to make things easier and clearer for us, I'm going to actually split this into two limits. So the limit as x goes to 0 of 1 minus cosine 2x over x times the limit.
Only do the x for two of them. Like why is it not like sine of x squared on the bottom of the x?
Okay, so this x that I'm multiplying by is not allowed to touch the argument. Okay, the argument, so this part right here, this is the argument of the trig limit or the trig function. You're not allowed to go in there at all. This x is not allowed to go inside with there. In order to go inside where the argument is, you would have to have a limit rule, a trig rule in order to do that. And I'm not using a trig rule. I'm simply multiplying by x over x. Okay, and again, it doesn't matter the order that we multiply in. I'm certainly able to work it like this. It's perfectly fine. Okay, because we're just multiplying everything straight across. All right, so yeah, we can't go inside the argument without a rule or an identity or law. So now the only thing I need is over here, I need to be 2 over 2. I'm multiplying by a clever form of 1 again. Why would I need a 2 there? Because I have to, so limit x goes to 0, 2 times 1 minus cosine 2x over 2x times the limit as x goes to 0 of x over sine x. Why do I need that 2 there? I need that 2 there because these things have to match. The 2x has to match the 2x. All right, so I've got 2 times 0, because that's a special limit that goes to 0, times 1, and my answer is 0. Now, just to kind of give you a little bit of comfort in that this trig limit lesson is one of the hardest ones in the unit. So if you're thinking, oh my gosh, she's gone crazy, it really is one of the hardest ones in the unit. And to be honest with you, we don't have a lot of trig limits that we have to do. Okay, so please don't think that this is all about trig limits. Again, we don't do a lot of trig limits, but trig limits are one of the more difficult kind of limits, I think.
How did you get the 0 and the 1?
Right here?
Yeah.
So this part right here, this piece right here, goes to this special limit up here, to this one right here.
Oh.
And that's why it turns to 0. Yes.
Well, how can your answer on this be the result is 0, but when you plug in the values and you get 0, 0, you cannot. Like how do you?
Because that's the special limit. That's the special limit that we will have memorized. This I outlined in green right here. That limit is this limit up here.
So there's no way that if you use the special limits and you get 0, that it's like that you're not done. Like if you get 0, you're always done if you're using the special limit.
You mean if my answer is 0?
Right.
Yes. Yes, you're done. Yeah, because the answer to that special limit is 0.
Oh.
So there's nothing else to do. Does that make sense? It's not 0 over 0. It's just 0. That's different. 0 is different than 0 over 0. Okay? They're different. 0 over 0 is an indeterminate form where 0 is just a number. Does that make sense? So it's not that we're getting 0 over 0. We're getting a true 0. Okay. All right, one more. You're like, oh my gosh, seriously? Okay. Trig limits, gotta love them. Okay, so again, several things you could do. Actually, it might be, I worked this out a different way. Well, I worked this out a different way. I multiplied by, are we all together? Are we all okay? Everybody listening? Okay, so I multiplied this by 1 over x over 1 over x because I wanted to get x under both of those signs. That's what I did. There's another way to do it that's probably easier, and that is using the double angle for sine. That's probably easier. But We'll do it this way. Okay. Because I'm trying to use the special limits. I'm trying to use the special limits. And actually, just for fun, maybe I'll do it the other way also. Wouldn't that be fun? Okay, I know y'all are like, please stop. Okay, so here we go. So in the numerator, I'm going to have sine 2x over x. In the denominator, I'm going to have sine x over x. Okay. Now, I can use my limit laws and just do the limit of the top and the limit of the bottom. Are y'all okay with that? Just do a limit law. Just make our lives easier. The limit of the top, limit of x goes to 0 of sine 2x over x over the limit of x goes to 0 of sine x over x. Okay. So the bottom one is ready to go. What's the answer to the bottom, the denominator? It's 1. It's 1. The top one is close, almost ready to go. What do I need? I need a 2. I need a 2 on the bottom, right? And with this little denominator, I need a 2. So I have to, and I can only multiply by the number 1. So I have to multiply by 2 over 2. Okay, I have to only multiply by the number 1. That's all I'm allowed to do. So let's rewrite this. Again, we are working on using our special limits. So 2 sine 2x over 2x over limit x goes to 0 of sine x over x. Notice, again, we have to have those spots match. Okay, the 2x has to match the 2x, the x has to match the x. When that happens, this part right here is the special limit. These parts are the special limit that I've circled. Those are the special limit, which is what? 1. So this turns out to be 2 times 1 over 1, or 2. Now that's using the special limit. So just for fun, because you know how I love trig, let's think about this using, let's say we just studied for a formula quiz. Do we know our double angle for sine? What is double angle for sine? 2 sine x cosine x. What could I do? Cross out. That's kind of nice. What is the unit circle value? What is cosine of 0? 1. This turns into 2 times 1 or 2. So maybe you would rather, remember the double angle, right? Didn't that make our lives easier? Yeah. I mean, there's always more, well, I won't say always. There's very often more than one way to solve these. Okay, this is just 2 different ways to solve the same thing. And there's our lesson.